Hello, in this video I'm going to be showing you an alternative way to come up with Pythagoras' theorem. Now, to use this alternative method we need to know Thales' theorem, okay, and that is if you put a right angled triangle inside a circle, right, where the diameter of that circle is one of its sides, then let's say for instance up here we're going to get an angle of 90 degrees. So let's prove this first. Let's prove Thales' theorem first. And then once we've done that, we can come up with the alternative proof for Pythagoras' theorem. So to prove Thales' theorem, we say that this length over here is r, this is also r, and this is also r. R stands for radius. What we can also do is call this angle over here A. We call this angle over here A. We can do this because this triangle to the left is an isosceles triangle. Okay. If this angle is A and this angle over here is A, then this angle over here in radians is going to be minus 2a, not a, okay? So this angle over here is going to be pi minus 2a. Because halfway around the circle, it's 180 degrees, or pi radians, it means this angle over here is going to be 2a, okay? And we can call this angle over here b, and we can call this angle over here b as well. Okay, now it turns out that 2a plus 2b, okay, is going to be equal to pi radians, okay, because pi radians is 180 degrees. But we can factorize this. We can say that's 2 times a plus b is equal to pi radians. Okay, and from here we can divide both sides of this equation by 2 like this. So we show that a plus b is pi over 2 radians, which is the same as 90 degrees. So we know that the angle over here, a plus b, okay, is going to be equal to 90 degrees. And if we know this, we can come up with the alternative way to prove Pythagoras' theorem. So what is the alternative method? Well, we get a circle again, and we put a right-angled triangle inside it where the diameter is one of its sides. Now, this large triangle is going to be made up of 3 other triangles, but the most important triangle is this one over here. We're going to call this length over here A. We're going to call this length over here B, and we're going to call this hypotenuse over here C. C is going to be the radius of this circle. So this means that this length over here is also C, and this length over here from here to here is going to be C minus A. Okay, so that is the radius, and you subtract A from that radius. Now, what's the next step? Let's call this angle over here theta. Okay, and we'll do the same for this angle over here. That means that this angle over here is going to be pi minus 2 theta. Okay, so this angle over here has to be 2 theta. This angle up here has to be pi over 2. Okay, that's 90 degrees, minus 2 theta. Now, because this up here is 90 degrees, this angle down over here is going to be pi over 2 minus theta. Okay, that is because, once again, this angle over here, all of this over here is going to be 90 degrees. Okay, so that leaves 90 degrees for the larger triangle. And if this angle over here is theta, then this angle over here has to be pi over 2 minus theta. Now, if this is pi over 2 minus theta, then this angle over here has to be equal to theta. Okay, and obviously this angle over here is going to be a right angle, and that's pi over 2 radians. Now, with all this information over here, it's going to be fairly straightforward to come up with the alternative proof for Pythagoras' theorem. Okay, next we're going to use Cho-Shikao to come up with the proof. So we have cot theta, okay, which is 1 over tan theta, is actually going to be adjacent over the opposite side. So we're using this theta over here to come up with this cot theta, okay, and that's going to be adjacent over the opposite side. So that is C plus A over B, okay? But we can also derive another cot theta, okay, using this angle over here. And that is also going to be adjacent over the opposite side, okay, because cot theta is 1 over tan theta. Now this will give us B over C minus A, okay, and these two things over here, these two cot thetas, are exactly the same, okay. So what we're going to do is we're going to make this equal to this, and we're going to derive a squared plus b squared is equal to c squared to complete our proof. Okay, so what do we have here? We have c plus a, okay, over b is equal to b over c minus a. Now this means, or this implies, that c plus a times c minus a is going to be equal to b squared, okay? Because we multiplied both sides of this equation by c minus a, and then we multiplied both sides of the equation by b, giving us this over here. And if we expand the left-hand side, we get c squared minus ac plus ac, which is 0, minus a squared, okay? And that's going to be equal to b squared. And from here, all we have to do is add a squared to both sides of this equation, and we prove, okay, that a squared plus b squared is equal to c squared. And this is Pythagoras' theorem. Now what I've done here is broken down this proof into bite-sized chunks so that you can understand it, but the same proof can be found inside the book, Proofs Without Words. That is version 1 by Roger B. Nelson, and this proof is inside page 8, okay, and it was found by a guy called Michael Hardy. Okay, so that is the Pythagorean Theorem 6. It can be found in Proofs Without Words, and I'll leave a link to this book just below this video. So if you're interested in purchasing this book, just visit the link below. I hope this video has been really helpful to you. If you want more mathematics proofs, make sure you're subscribed to my channel. Thanks for watching, and see you in the next video. Oh, and I forgot, for more maths content, visit mathematics.proofs on Instagram. Thanks for watching.